Section 5.2 is going to talk about some sum and difference formulas for sines and cosines. And so notice that when we talk about the sum and difference formula, the sum or the difference is happening inside of the function itself. So this would not be the same thing as the cosine of alpha plus the cosine of beta. This would be take the alpha and beta and add those two angles together and then take the cosine of the remaining angle. Well, sometimes that doesn't give us something that's very useful. And so what we have is we have these sum and difference formulas for sine and cosine. Now, here's kind of how I remember how to use these. The cosines, you pair the same functions together. So notice it's cosine, cosine, and sine, sine for the two products. But then for cosine, notice that the sine is opposite. So if I'm doing the cosine of a sum, I end up taking the difference of these two products. If I'm taking a difference inside my function, then I really end up adding what I get there. Now with sine, the part that switches is that you pair up a sine and a cosine in each one, okay? So it starts with sine, cosine, and then cosine, sine, but here the operation remains the same, plus, plus, minus, minus, in that kind of a way. You don't have to have these memorized. They're on the reference sheet that I've given to you, so as long as you know how to use them, you'll be in good shape. So what do we use this for? Well, let's say that I want to find the exact value of the cosine of 15. Now remember, when I've said exact value, I said that means one of two things. You're either pulling a value off of your unit circle, or you're setting up a right triangle. Well, 15 degrees is not something that I know on a unit circle. And since I also don't have like an opposite over adjacent or some sort of ratio to set up a right triangle, this is how I know that I need to aim for something that's on my unit circle. So I need to think of two angles that I could add or subtract on my unit circle to come up with 15. So we want to be thinking about angles like 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so on. So the way that I'm going to choose to set this up, and there is more than one way to do it, but the way that I'm going to consider this is as the cosine of 45 degrees minus 30 degrees. Okay? So by doing that, that makes this alpha and this beta. That's determined by the order. It's got to be the cosine of alpha minus beta. And so now I just use the formula that I have. So the formula for cosine is cosine, cosine, sine, sine. And then because the cosine is subtracting, I'm going to have a plus in my formula. So this is going to be the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the cosine of 30 degrees. Okay, and we get these off of our unit circle. So the cosine of 45 degrees, that's pi fourths. That's going to be the square root of 2 over 2 times the cosine of 30 degrees, which is square root of 3 over 2. Again, these are just off of our unit circle. Plus sine of 45, also square root of 2 over 2. And then the cosine, oops, I wrote this one wrong. Sorry, this should be a sine. You probably were wondering that when I wrote it. So the sine of 30 degrees is 1/2. Sorry about that. Make sure that you check that out. That should be a sine, not a cosine. And so now we just need to simplify this down. So I can multiply radicals, and I multiply fractions straight across. So this gives me the square root of 6 over 4 plus 1 times the square root of 2, which is just the square root of 2 over 4. And we can put all of that together to be the square root of 6 plus the square root of 2 over 4. That is the answer in its exact form. If they ask you to round, then you could round. But exactly means not using your calculator. Okay, so let's look at one that goes in reverse. So we want to find the exact value of cosine 80 degrees times the cosine of 20 degrees plus the sine of 80 degrees times the sine of 20 degrees. Well, notice this goes cosine, cosine, sine, sine. So that tells me it's got to be one of these two on the top. It's got to be a cosine. And then I look at the sign in the middle and see that that's plus. So I know, since this is cosines and sines that are paired, and because this is a plus, I know that this has got to be cosine of alpha minus beta. Well, this would be alpha, this would be beta. So I want to do the cosine of 80 minus 20 degrees. That would be cosine of 60 degrees, which again, we go to our unit circle and we know that that is 1/2. And so that is how that one would work there. All right. So we can use this to verify identities as well. So these are, we're kind of adding on to whatever we've got. So I have the cosine of alpha minus beta divided by sine alpha cosine beta, and we want to show that that's equal to the cotangent of alpha plus the cotangent of beta. So here's how I would run through this one. First thing is, let's substitute out for that difference formula there. So cosine alpha cosine beta, or minus beta, would be cosine alpha cosine beta plus, because the sign is opposite, sine alpha sine beta. And that's all divided by sine alpha cosine beta. And now there's no GCS to factor out, and I can't start canceling anything because this is all connected together. We can only cancel factors, and I don't have any factors. So really our only option at this point is to break our fraction apart. So let's split this up to be cosine alpha cosine beta over sine alpha cosine beta plus the sine of alpha and the sine of beta divided by sine alpha cosine beta. And now we don't have a plus or minus in the numerator of our fractions anymore. These are all just factors. So we can start dividing some stuff out. So cosine betas divide out here, sine alphas divide out here. And if we look at what we have left, cosine of alpha over sine of alpha, they're both alphas, so we can use those. If I have that, cosine over sine, that's going to give me the cotangent of alpha. Plus, over here, again, I have beta and beta, so now I have sine beta over cosine beta, which is tangent beta. And so we got what we wanted. So there is a way that we can kind of involve these in our identities now. Let's look at one that's in radians because it's a little bit trickier with the fractions, but other than that, it's fine. And they were kind to us here on number 4, and they said, find the exact value of the sine of 7 pi twelfths, knowing that 7 pi twelfths is equal to pi thirds plus pi fourths. Now, how would you know that that was pi thirds plus pi fourths any other way? Well, the way that I would kind of think about this, if I'm trying to determine how I can break this up, is I know that I've got to have a common denominator. Something over 12, something over 12. These are my pi's. I want to pick values that are going to reduce down because twelfths is not a number that I know. So, could we have picked 6 and 1? Sure, 6 pi twelfths, that's pi halves. I know what to do with that. But 1 pi 12th, I don't know what to do with that. That's not a value that I know exactly. So that won't work. So maybe we try something else. 5 and 2. Well, 2 pi over 12, that reduces to pi sixth. I know that one. But again, 5 pi twelfths doesn't work. So we're back to the drawing board. We need to get 2 values that we know. So if we try something like 4 and 3, those are both going to reduce down. 4 pi over 12 gives us pi over 3, and 3 pi over 12 gives us pi over 4. So since I found 2 values that reduce to something I know that that's how I want to split apart this fraction. So it just kind of depends on what you're given, how you're going to, set this up, okay? So if we want sine of 7 pi twelfths, and we're going to split this apart in this way, that makes this a sum. So pi thirds is my alpha, pi fourths is my beta, and the formula here is going to be sine alpha cosine beta plus, cosine. Now I have to switch. I already used the sine for alpha. So now I have the cosine of alpha times the sine of beta. Notice that if I look across the whole thing, I have a sine and a cosine for alpha, and I have a cosine and a sine for beta. You got to have one of each. And then the sine stays the same there. So now we can plug this in. Sine of pi thirds times the cosine of pi fourths. Plus the cosine of pi thirds times the sine of pi fourths. Sorry, that probably hurt your ears right there. So the sine of pi thirds, again, we go to our unit circle. Sine of pi thirds is square root of 3 over 2 times square root of 2 over 2 plus the cosine of pi thirds, which is 1/2, times the square root of 2 over 2. And you can see, again, we're going to get a common denominator of 4. So we end up with, oddly enough, the same relationship that we did on the first problem. Square root of 6 plus the square root of 2 over 4. You cannot combine the square root of 6 and the square root of 2. They're not like terms. Remember, radicals have to be like radicals. Same variable, same radicand, same index. You got to have all those same things. We don't have the same radicand. One's a 6 and one's a 2. So that's it. We are done. Okay? So the process is the same even if you're working with radians and you're working with fractions. It just makes it a little tricky to decide how to divide it up if they don't tell you how to do it in advance. So the last kind of thing to look at here with sines and cosines is, like I said, we are always looking either at the unit circle or at right triangles when we're talking about the exact value. So here, they're not giving us the angle. They're giving us the ratio. That tells me that I'm going to be looking at right triangles, not my unit circle. So I know that the sine of alpha is 12 over 13 for a quadrant 2 angle alpha. Remember, the quadrants are important because they tell us about the sign of our angle, whether it's going to be positive or negative. And then the sine of beta is 3 over 5 for a quadrant 1 angle beta. So we want to find the exact value of each. Now, before we can find cosine alpha, cosine beta, and then the sums, we need to know what the triangles are that we are working with. So remember that sine is opposite over hypotenuse, or you can think about it as y over r. R is the radius, which is your hypotenuse. And since we're in quadrant 2, I like to go ahead and set up my picture according to what that would look like. So quadrant 2 is going to be over here like this. So I'm going to be looking at some right triangle over here in quadrant 2. Okay, so alpha is always going to be here on the inside, or theta, or whatever the angle is. Opposite is 12, so the 12 is going to go here. And hypotenuse, or r, is 13. That's going to go here. Now, the reason why the fact that this is in quadrant 2 is so important is because it tells us about our signs. The y is positive in quadrant 2, but the ordered pairs look like this. So that means that whatever we get for this side, it's going to be a negative number. And you can use the Pythagorean theorem to figure out what the x is. So we'd have x squared plus 12 squared equals 13 squared, but you may already recognize that this is a Pythagorean triple. So negative 5 is the value here. Okay, now let's do the same thing for beta. Beta is in quadrant 1. So we'll set that up over here. We'll have a triangle that looks like this. In quadrant 1, ordered pairs are positive, positive. So that means our x and our y are going to be positive, and then beta is going to be right here. So again, they gave us sine. So that's opposite over hypotenuse. Now the hypotenuse is 5. So that means, again, this is a Pythagorean triple. This will be 3, 4, 5. But if you don't know your triples, just use the Pythagorean theorem. 3 squared plus x squared equals 5 squared. And a side note to make here is the Pythagorean triples only work if the biggest number is the hypotenuse. We had one on the test where the two sides were 3 and 5. And a lot of you decided that the hypotenuse then would have to be 4 to make 3, 4, 5. But that doesn't work. 5 would have to be the hypotenuse because it's always the longest side. Okay, so we have the triangles set up, and now we can start working on answering the questions. So A wants to know the cosine of alpha. Well, cosine is going to be x over r, or adjacent over hypotenuse. So that means that the cosine of alpha, we need to go to our alpha triangle, which is the top one. So adjacent would be negative 5 over the hypotenuse, which is 13. So there's that. B, we need the cosine of beta. Sorry, there goes the bell again. It's lunchtime. So the cosine of beta, now we got to go to our beta triangle. and we see that adjacent is 4 and the hypotenuse is 5. So cosine of beta is 4/5. Now we know sine of alpha and cosine of alpha. We know sine of beta and cosine of beta. So now we can start working on C and D. We cannot answer those questions until we know both. Because remember, the formula for the cosine of alpha plus beta is going to be the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So I got to know sine and cosine for both. But we know those values, we just figured them out. So cosine of alpha, we just determined was negative 5/13 times the cosine of beta, which we also figured out was 4/5. Okay, minus the sine of alpha, that was given to us, it's 12/13, times the sine of beta, which was also given to us, 3/5. And now we're just crunching numbers down. So 13 times 5 is 65. So I get negative 20/65 minus 36/65. That comes out to negative 56/65. And I don't think that can be reduced. You should always check. But, nope, that is it. So negative 56/65 is the answer for the cosine of alpha plus beta. Even though we don't know what alpha and beta are, notice we never found the angles. We just know the relationship with the sides, and that's what we had to use our right triangles for. So now we can work on D. The sine of alpha plus beta is going to be sine alpha cosine beta plus cosine alpha sine beta. And again, we just substitute. So sine alpha was given, 12/13, times cosine beta, that was one that we figured out, 4/5, plus cosine alpha, which again we figured out, negative 5/13, times the sine of beta, which was given as 3/5. So we have 48/65 minus, because this is going to end up negative, 15/65, and so all together we come out with 33/65, and that is our answer. Okay, little more work involved with those. You got to set up your triangles, but once you get it, it's just plugging into the formulas. Okay. Alrighty, the last thing to show you here is the sum and difference formulas for tangent. These are a little bit uglier, okay? Now, you can verify this identity here. I will post this on the notes with this one worked out. But what I would rather do is work one out where we need to actually evaluate the tangent, because these can get a little bit messy sometimes. So, I'll move this down. Let's do a subtracting one. So I'm going to, instead of doing this example right now, we'll do something different. So for number 6, see your notes. For number 7, we'll add a problem on here. See notes. And you can practice that identity on your own. You can probably figure that out pretty easily if you just make the right substitution. But let's do the tangent of, let's just do 15 degrees since that's an easy one. We already know what the value is going to be here, okay? So tangent of 15 degrees, let's think of that instead as the tangent of 45 minus 30 degrees, because that would be equal to 15. Well, that makes 45 alpha, and that makes 30 beta. So since this is subtraction, we're going to use this tangent formula that you see up here. So let's just substitute and set this up. So the tangent of alpha is going to be the tangent of 45 degrees minus the tangent of beta, so that's going to be minus the tangent of 30 degrees, all over 1 plus their product. So the tangent of 45 degrees times the tangent of 30 degrees. Okay. So you got to know your tangent values to work this one out here. Tangent of 45, that's an easy one, that's 1. Minus the, tangent of 30 degrees, which is square root of 3 over 3. over 1 plus 1 times the square root of 3 over 3, because we multiply the values this time. So you'll notice this is where these get pretty gross. Okay, we have 1 minus the square root of 3 over 3 divided by 1 plus the square root of 3 over 3. Now there's two problems with this answer right here. One, I have fractions inside of a fraction, so we have a complex fraction. We need to work on getting a common denominator and then multiplying by the reciprocal, keep, change, flip. So we have to simplify that first. And then number two is we need to rationalize. We can't leave radicals in the denominator. So we've got some work to do here with this guy. So let's start first on our common denominators. 1 is going to be 3 over 3. So we can get that common denominator pretty quickly. This is going to be equal to 3 minus the square root of 3 over 3 divided by 3 plus the square root of 3 over 3. And then if we keep, change, flip, I'm going to put this down here actually, we're going to have 3 minus the square root of 3 over 3 times 3 over 3 plus the square root of 3 over 3. There's a lot of 3's. These will divide out. And so now we have 3 minus the square root of 3 over 3 plus the square root of 3. So step 1, check. We have gotten rid of the complex fraction. We still have an issue here, though, because this needs to be rationalized. So if you remember from before, maybe you don't, but the way that you rationalize this is to multiply by the conjugate, which would be the opposite sign. So this is going to be 3 minus, oops, I switched colors, the square root of 3 over 3 minus the square root of 3. It's the conjugate because we do the opposite sign of what I have, and we're working on the denominator to rationalize. So now we end up with, FOIL out the numerator, and I'm going to get 3 times 3, which is 9, and then minus 3 root 3 minus 3 root 3 plus the square root of 3 squared, which is going to be 3. And when you multiply by the conjugate, that's a difference of squares. So we're going to get 3 squared minus the square root of 3 squared. Well, the square root of 3 is just 3. So in our numerator, we have 12 minus 6 root 3 over 9 minus 3, which is 6. Sorry, you can't see that under here. That's a 6 down there. This is so close to being done, but now we can divide all 3 of those terms by a factor of 6, so we get 2 minus the square root of 3. That is what this all comes down to. So the tangent ones can get pretty ugly. They are long, like this problem was a little bit tedious, but other than that, it was just straight algebra. It's just getting these algebraic computations down. You have to go step by step. So to get rid of the complex fraction, you got to work on common denominators and keep, change, flip. And then lastly, you need to rationalize the denominator. So make sure that you do that. Okay? And I believe that that is the end. It is. So there's an assignment on my math lab. You can get started on that, and I will be around for questions when I see you next week.